this is a particle in an empty space. There are no forces acting on it. So as we know from Newton's first law, relative to any inertial frame of reference, if there are no forces acting on an object, then the object won't have any acceleration either. So if f equals to 0, then a should be 0. And our particle here also doesn't have any acceleration. Now, since there are no forces and no acceleration on the particle doesn't have any velocity either. So the particle doesn't really move, it's just stationary in an empty space. All of this sounds good, right? We have a particle, it's in the middle of nowhere, and there is no forces on it. But ultimately we do want some forces. We want the particle to move. We want a simulation. And when we do simulation, we usually have forces, velocities, etc. So let's say we add some force into this. And let's say there is a wind force, there is also probably a bit of gravity force, and our particle should move. But before we do anything with the forces, we need to determine where the particle is. And this is very important because the particle should be in some sort of space, in some sort of atmosphere either, or maybe underwater, or maybe in some sort of a gas, some sort of a fluid. The medium is extremely important because this medium will ultimately determine what kind of drag forces will be applied to the particle once it starts moving. So let's say due to all the forces, our particle has some velocity v. But also remember, since the forces aren't constant, for example, maybe the wind has turbulence, our velocity isn't constant either. So it is changing over time, right? So dv by dt, or changing a velocity over time, is acceleration. Now just like Newton's first law, our particle has some acceleration, as the net force acting on it is not 0. So if the net force is not 0, there will be some acceleration, and that means that the particle will have some velocity that is changing over time. So now when our particle moves with some velocity v, there will be some linear or quadratic drag. Like I mentioned before, this drag force totally depends on the medium. Like if the particle is inside honey, or if the particle is inside some gas or air, then the drag forces will be very different. But there will be some drag forces, and let's say we have a linear drag and a quadratic drag together. So if we combine both linear and quadratic drag forces acting on the particle, we will get this equation, that is dv by dt equals to minus a v minus vt minus b v minus vt square multiplied by v minus vt divided by v minus vt. So as you can see in this equation, there are certain parts of v minus vt that are inside two bars. So that means that these are just the the magnitude and not the direction. So these are basically scalarized. Okay, and the one v minus vt that isn't between two bars, that is the whole vector. So that has direction and magnitude. The others are just scalarized and they don't have any sort of direction. It's just a magnitude. Also notice that this is an equation of velocity that is changing over time. So dv by dt. So that means this is an equation of acceleration. Also in this equation we have some variables like a, b and vt. So what are these? So a and b are linear and quadratic drag coefficients. So basically with a and b you control how much linear or quadratic drag you want to affect on the particle. And vt is the relative velocity. So probably a velocity of the wind around the particle, or if the particle is in water, velocity of water that's flowing around the particle. To get the acceleration of the particle, we need to subtract the relative velocity of the medium in which the particle is moving from the actual velocity of the particle. That's why v minus vt. To simplify the equation, if we say v minus vt equals to v, then we get this equation, dv by dt equals to minus a magnitude of v minus b magnitude of v square multiplied by v divided by magnitude of v. Now to simplify this whole calculation even further, we can just work with the magnitudes only. So that means the speed instead of a velocity. So if we scalarize all the v in this equation, what we get is dv by dt equals to minus av minus bv square. Now notice that here, although I say av and bv square, this v is basically the magnitude of the vector v. So this is basically speed. So if we code this, or when we code this, we won't write this v as a vector. Rather, we will write this as float, because this is v, the speed, not the velocity, the vector. So this is our simplified equation for velocity or speed changing over time, or the equation of acceleration. As we know, if we find out the area under the curve of this equation, we will get the velocity equation. Now, this is a very general acceleration curve. Okay, now there can be multiple acceleration curves based on the value of a or b, but doesn't matter what the acceleration curve is. If we want to find out the velocity from the acceleration curve, the method is to find out the area under that acceleration curve. Now this is the territory of calculus, where this is basically calculus only, where calculus says that if you find the area beneath the acceleration curve, you get a velocity, and if you find the area beneath the velocity curve, you get the distance that an object has covered. So now here we have an acceleration curve, and if we do some integration on it, then we will get the velocity curve. So before we do the integration part, we can actually change this equation a little bit, make it a little bit more easier for us to integrate. So if we switch around our variables a bit, we will get 1 divided by v into av plus bv into dv equals to, on the right hand side we get minus dt. Before integrating this equation, we can go a bit farther. We can also perform a partial fraction decomposition on this. So if we perform a partial fraction decomposition, I'm not going to show either the integration or the partial fraction decomposition, because that is purely maths and that is beyond the scope of this video. Also, that will make this a video unnecessarily long, because it's difficult to show maths in a video, I guess, unless you are doing it on a blackboard or any kind of board. So after doing the partial fraction decomposition, we get 1 divided by av minus b divided by a into a plus bv into dv equals to minus dt. So now let's do the integration, right? So if we do the integration, the ultimate result that we'll get here, not the ultimate actually, the result of the integration that we'll get here is 1 by a log of v minus 1 by a log of a plus bv equals to minus t plus c. Now this c is a new variable. Basically it's a constant. It's not a variable actually, it's a constant. So if you integrate something, you get a constant. Now someone who knows integration will say that if we are integrating left hand side and right hand side, we should get two constants. And that is true. We can write c1 and c2, that is basically two constants, one for left hand side, one for right hand side. But ultimately that won't make any difference, because ultimately we are going to ignore the constant. So it doesn't matter how many constants you write. So here, for the sake of this argument, I have written just one constant plus c, but you can also write two constant. And if we further go into this equation and make this even more simple to code and ultimately merge all the constants, we will get v equals to k into e to the power minus at into a divided by 1 minus k into e to the power minus at into b. And if we ignore the constant k here and ignore all the initial factors like initial velocity, initial time, everything, then we will get v equals to a divided by e to the power at minus b. So this is the most simple form, or the simplest form that this equation can get. So it is always advisable to get your equation to the simplest form before you start coding. So we can code this. In Houdini, we have an exponent function for e. Most people probably haven't used the exponent function or exp, or probably you have, I don't know, depends on what you do with Houdini. So we have e. We also have the variables a and b. So basically a and b we will determine ourselves. Okay, so we can just put any kind of values in a and b and see how the drag works. And a is your, as I said, linear drag coefficient, b is quadratic drag coefficient, v is a velocity, and t is your time. But here is the thing, when we say t is the time, what kind of time? What do we mean by time? We cannot just add at the rate frame. That won't work because the frame numbers will change. You can have different frame numbers. That won't work. So time has to be in seconds. But also in this case, when we say t equals to time, we need to look at the fact that how much time has passed in every time step, right? So for our new velocity here, or since we have scalarized everything, our new speed here, that we need to figure out the velocity or the speed in each time step, at the end of each time step. So by time step, I mean subframes. So when you do a simulation in Houdini, you have substeps, right? So sometimes you do one substep, sometimes you do 10 substeps, sometimes you do 20 substeps. So this time is totally dependent on substeps. So what we will do while code is we will have a t0. So t0 is at the beginning of the substep, and a delta t, which is your time increment. So in Houdini, we have an attribute called time increment. Okay, if you are doing in any other software, so you might have something equivalent to this. So time increment is basically 1 divided by FPS, whatever your FPS is. So in Houdini, by default, it's 24 FPS. You can change the FPS, but the best way in Houdini is to use the time increment. So what we will do t0 plus time increment, or dt. But we do not know what t0 is, right? We know what time increment is because in Houdini we have an attribute called time increment, and it does give us a value of time increment. But we do not know what t0 is. So we need to figure out what t0 is to plug in a value of t0 in this equation. So now if we try to get the value of t0, because we do not know t0 is, we can replace v in this equation with v0 and t in this equation with t0. Now what is v0? We haven't mentioned v0 yet. So v0 is the speed or velocity, depends on whether you scalarize this or not, but we have scalarized this. So the speed of the particle at the start of any time step. So when you are right at the first frame, right at the first time step, when the simulation is just starting, v0 will be 0 because the particle has no velocity. So it will be 0. But if it's, let's say, in frame 3, frame 4, or some frame in the middle of the simulation, v0 will have the value of the previous time step. Notice, not previous frame, previous time step, because your simulation has substeps. So v0 will be the value of previous time step and not previous frame. And so if we now take the now try to solve this equation and get the value of t0, what we will get is 1 by a into log of a plus v0b divided by v0, where v0 is the speed of the particle when it just gets into this time step. So, or basically v0 is the speed of the particle in the previous time step, right? So now for our v equation, notice that this v equation is the velocity for the particle in this time step, and the v0 is the velocity of the particle in the previous time step. Okay, so now in this v equation, which is the velocity of the particle in this time step, we can write a divided by e to the power a t0 plus time increment minus b. We can also write time increment as delta t, but since we are pretty close to coding this in Houdini, we can also write it as time increment. So now here comes the Vex part. It's not very long actually. If you try to solve all the maths, I suppose the maths will actually be longer. This is the main reason why I didn't solve everything line by line, because it's quite long. But the Vex part isn't very long. It shows here around 60 lines, I guess, something like that. But I have also left line gaps in between, so it will be something like 30 to 35 lines, I guess. Anyway, so this is the Vex part. at first I initialized all the variables here, as you can see. Notice I'm also initializing a and b variables, which are once again linear and quadratic drag coefficients respectively. I also add force with my incoming velocity using Newton's second law, F equals to ma. Now this is important, because if I do not do this step, then the solver will definitely work. But every time you have, if you want to add some force, right, if you want to have some rotational force or anything, Houdini's DOP network has a lot of pop micro solvers, and a lot of those micro solvers are forces, right? So if you want to add gravity or any sort of pop micro solver force, this Vex code won't recognize it because it doesn't know what to do with that force. So it is important that we add that force in our solver. And how do we do that? We use Newton's second law, F equals to ma, force equals to mass into acceleration. Notice that I've also initialized mass here. So, when we do pop simulation, we create a mass attribute. So the same mass attribute you can use here also. So I've done that. Then I subtract the target v, or the reference velocity of the medium, and get the length of the velocity to scalarize it for our calculation. So this target v here, it's 0 basically, but I still subtracted it because, as I said in the beginning, to do the calculations we need to remove the velocity of the medium from the velocity of the particle. So we subtract this. So if you are maybe doing particle inside water or particle in a flowing wind or something like that, you might have some target v attribute. Target v, you can also use this in Houdini's pop solver. So this solver that I am showing here, it is very similar to Houdini's solver. It's basically the same algorithm, just that the calculations are a bit different. They did the integration a bit differently. I am doing it a bit differently, but the algorithm is more or less same. So if you go into Google and search target v Houdini pop solver, you will get something in the documentation. So that's the same thing here also. So now we here show our v0. So v0 is our incoming velocity, right? The velocity before doing anything. It is the initial velocity at every time step, as I have explained before. V0 is basically the initial velocity at every time step. Now in this large if statement, as you can see, there's a big if statement. I have created 3 variations. Okay. So since the beginning of this whole video, I am saying that we are using both linear and quadratic drag, both linear and quadratic. Always I am saying this thing. But in a particle simulation, you can also use either a linear drag or a quadratic drag, or both together. So if you use either a linear drag or a quadratic drag, okay, the maths become a lot more simpler. But I used both together because that gives more accurate results. And I'm not a master of physics here, but I have heard professors often say that when you go at very high speeds, when the forces are extremely high, particle can, be affected by both linear and quadratic drag. So let's check if our solver matches with Sidefx solver. So as you can see in this screen grab, the white particles are Sidefx's, the red are mine, and they match pretty well, right? But this is just a few particles and it's not fun. So let's test it on millions of particles. So here I have a simulation with around 10 million particles, and it works pretty well, I guess. But you have to also remember that this is a pretty bare bone basic solver. It doesn't have collisions. It doesn't have anything to deal with rotation, angular velocity, or anything like that you might use in the fully fledged pop solver that Sidefx has. But it gives you a basic idea how simulations work, or how particle simulations work in general. And I want to also mention this, that you can do a particle simulation without doing any of these things with a very simple Euler integration method, and that is good. But the reason why Sidefx went this far and they made it this complex is because Euler integration methods aren't very accurate when it's a lot of particle and or a lot of forces. Okay, so this is the main reason for doing it this complex. Now at the end of my Vex code, you can see that I am adding the velocity with position, and that method is basically Euler integration only. So for that part, so it's not like you cannot just code until creating the velocity and then leave it. Houdini doesn't know what to do with the velocity. You have to convert that into position. So from velocity to position, that you can do with Euler integration or any other integration method like Verlet integration, which is a better integration method. So maybe some point I will do some tests with various integration method and see how it goes. But yeah, that's it. Also, it's a very bare bones solver and it looks pretty cool, I suppose.